3 lightning talks. So I take the opportunity right now to make a couple of announcements. The first announcement is for the people who are staying in Ontario Hall. Unfortunately, we have been noticed that the people are not properly wearing the mask in Ontario Hall. So I remind you, it's compulsory, unless you're eating, it's compulsory inside the university to wear the mask all the time. And please do it here, but do it also when you are in Ontario Hall, when you are in your residence. The other information is that, well, I hope yesterday you have a nice night out. If you want to do this again, so join some dinner downtown with the other participants, you can sign up there. So possibly, if you can do it today for the dinner tomorrow, that would be great, so we can confirm the reservations. And of course, for tonight, we are all set because we have the conference dinner that will be in Times Hall that is here in the campus nearby. We will give you information later about how to go there. So at this point, I'm ready to leave the floor to Andrea, who is affiliated with the Vienna group.
Yes.
And so please, Andrea.
Yes, thank you. So I'm very excited to open this session about the limitation of objectivity given by quantum mechanics, because we talked about a lot of things, but somehow this theme hasn't been touched upon, because we talked about how quantum mechanics puts strain on our notions of causality, causal ordering, and we didn't even touch on how it puts limits on the notion of determinism and like our limit of knowledge in the world. I think we're kind of used to it now. But there is a new development in the recent years about how quantum mechanics actually can put a constraint on our idea that we share an objective reality together as observers. And I will talk to you about this. And it all starts with Wigner's friend experiment. And it goes something like this. So I have a friend, it's Emanuele. He's a very good experimentalist, and he's in his lab, in his photonics lab. And he's considering a source of single photons that emits photons in a superposition of polarizations. And he sends this to a beam splitter, and he knows exactly what's going to happen, that he's either going to detect the photon in one branch or the other branch, and he sees a definite result on his computer screen. But I'm not an experimentalist. I'm sitting at home, and I'm thinking about Emanuele. And Emanuele is made of atoms, I'm thinking, and the computer is made of atoms and so on, and these things satisfy quantum mechanics. And although I have no ambition of actually knowing the quantum state of the lab, I assume that there is a quantum state. And using the linearity of quantum mechanics, I can time evolve this state. I know what happens. I know what would happen in the other case of polarization. And I evolve this, and I get this entangled state, this superposition. And I might be confused, like, is Emanuele in a superposition? And, what does it feel like for Emanuele to be in a superposition? And then we think a bit more, and whenever I go to the lab, I see Emanuele in one specific state. So I might think, okay, it's just that I don't know what Emanuele saw, and the difference in description just comes from my ignorance of the situation. And this is kind of the setup of Wigner's friend scenario, and depending on your reading of quantum mechanics, you can be more or less confused about this. But then things change. And this is a setup proposed by Caslav Brukner, where it changes when, instead of having one friend, we have two friends in the lab. And instead of just thinking about the friends, we imagine that here we have Alice and Bob, and they're thinking about their friends, Charlie and Debbie. But they're not just thinking about it. We assume that they have full quantum control on the lab of their friends. And if we ponder this situation, specifically in the situation where Charlie and Debbie are not just measuring a single state, but they're measuring an entangled state, we can get something really strange appears. And this is the focus of a no-go result, no-go theorem. So here we have a space-time diagram of the situation, where C and D are the outcomes of Charlie's and Debbie's results inside the C of the labs. X and Y are the choices of measurement that Alice and Bob can do. And A and B are the outcomes of these measurements. Now, these measurements in certain cases can be something as simple as asking their friend what happened, they see what it is. But in other cases, because we assume that they have full quantum control, sometimes this measurement might involve rewinding the history of the lab, which is a bit extreme, not a nice thing to do to your friends, but quantum mechanics says it could be possible. So what we always observe are these frequencies, the frequencies of the outcomes A and B, given the choices of measurements X and Y. And sometimes, so most of the time, we don't see what C and D actually were. But let's say that we assume that our friends have an outcome of the measurement. It's just that we don't know about it, the same way I was doing before with Emanuele. Then we might postulate that there is this probability distribution that explains the probability distribution A and B. So this one without the tilde, but it's explained by this other probability distribution that involves the outcomes of Charlie and Debbie. If we then also assume no superdeterminism, so the idea that the choice of Alice and Bob does not depend on the outcome of the measurement of their friends, and on top of that, we assume locality, which in this case means specifically that Alice's outcome does not depend on Bob's choice of measurement, even when we consider what C and D were. Then, in a manner similar to Bell's theorem, we can derive a set of inequalities that constrain the possible probability distributions FA, B given XY. And the striking result is that they're called local friendliness inequalities. It's just a word, just a name for them. They are incompatible with quantum mechanics. And so this means that assuming full quantum control is possible for arbitrary systems, which we have for now no reason to doubt it necessarily, we have to give up one of these three ideas. And I want to compare this to the setup with Bell's theorem, because these assumptions of no superdeterminism and locality were part of the first Bell's theorem, which included also this notion of predetermination that people called also realism. So when people say Bell inequalities show that the world cannot be locally real, this is what they're referring to. And to save locality and to save superdeterminism, most people say, okay, well, the predetermination is false. There are no outcomes of measurements before doing the measurement. And so this kind of resolves the tension of Bell inequalities. Then there's a second theorem of Bell, which involves a different notion of causality, which is local causality. And we've been discussing this a lot yesterday and today also, the idea that if two sets of events are correlated, then one can explain this correlation by looking at a common cause, which is in their relativistic past, meaning in their past light cones. There is an event that if you condition on that event, you can remove the correlation between them. And again, here, to not accept superdeterminism, most people give up local causality. And yesterday, we talked about what the consequences of these are. And I think, in part, we discussed about two deeper principles. So the idea, the relativistic causal arrow, which is exactly that the cause has to be found in the special relativistic past of both events, and that it points from the past to the future, containing both of these ideas. And the other principle is Reichenbach's principle, that somehow an explanation is this idea of removing the correlations when you condition on the cause. And I think it's fair to say that we were mostly considering eliminating this idea giving up this idea of explanation in terms of Reichenbach. And the situation now is interesting because this thing that we did to save locality doesn't really help us to reconcile quantum mechanics with the violation of the local friendliness inequalities. Because we gave up predetermination to save locality, but now locality is again in question, together with this idea of absolute events. And of course, absolute events was also a precondition for Bell's inequalities that were normally left unsaid because it looks so obvious that we share somehow an objective reality. So we're in a situation where we have to decide what to do. And I think this is really interesting. One way to think about it is that this naive way of thinking that there exists a classical world where experimenters have definite outcomes of measurements is not compatible with quantum mechanics. So this, what sometimes is called the no interpretation of quantum mechanics, has to be revised. We have to think a bit more. And one way to do it, obviously, is modifying quantum mechanics, saying, well, not all systems can be put in a superposition. And this is the way with spontaneous collapse theories or ideas where like observers cause the collapse of the wave function. And then it's important to note also that Bobian mechanics satisfies the Bell inequality, goes around Bell's theorem and around this theorem the same way by giving up locality or relativistic causality, to be more precise. And so do superdeterministic theories, of course. The other way is to give up the idea of absolute events and accept the idea of relative facts. And the second part of my talk is about an interpretation that does this, which is the relational interpretation of quantum mechanics, also known as relational quantum mechanics. And this interpretation was proposed by Carlo when I was a kid, basically. And yesterday I was rereading the abstract, and it's really interesting because a lot of the ideas that we discussed in the past few days are inside this abstract. In particular, there is this idea of the reconstructing quantum mechanics from fundamental principles. There is this idea of understanding quantum mechanics in terms of information theory. And finally, related to what we're talking about this afternoon, in the abstract, Carlo says, well, maybe the incorrect notion that is confusing us about quantum mechanics is this idea of observer-independent values of physical quantities, right? So introducing this idea of a relative value or a relative fact. And there's a few guiding principles for relational quantum mechanics. I think in the last years, it's been changing a lot. It's gaining a bit more attention by the literature. But there are some few things that are stable, let's say. So one of the ideas is that we shouldn't modify quantum mechanics, that we should keep both unitary evolution and the Born rule, and they're both correct to all levels. There's this idea of relationalism, somehow that reality is made out of an interaction between systems, that things don't exist on their own, independent of everything else. There is this notion of perspectivalism, so to describe the world from inside space-time, not from outside, and in terms of, and also to have different observers seeing different things. The idea that there are no special systems, no things called measurement apparatuses, or no systems that behave different from quantum mechanics, or conscious agents doing something about the wave functions and so on. There are no inaccessible realities, like everything is there to be measured. There are no hidden variables. There are no parallel worlds. And also want to stay close to relativistic ideas and ideas of time symmetry. This is kind of general things. I think, but to be more concise, more precise and concise, like what I think about relational quantum mechanics, I think about these 4 ideas. So one idea is that when systems interact, the variables of these systems take values with respect to each other. So for example, the spin is up, I get a kick with a certain momentum, and stuff like this. And this is what builds reality, these interactions. And the quantum state is used as a calculational tool by the physicists to calculate probabilities of certain facts given other facts. So the quantum state evolves unitarily until I get a new kick and I change the quantum state. But what's important here is that these kicks, these values, are relative facts. They're relative to the systems. And so, for example, Emanuele is in the lab and he sees this computer showing 0, and that's a fact relative to him. I am outside, and what I see is this 4th idea that I don't have a fact relative to me, and I'm describing this as an entangled state. And as Carlo pointed out earlier, all it means to have entanglement and to have superposition, it all transpires in terms of probabilities of what we expect to see. So I expect to see correlations between Emanuele and the photon, but I don't know what happened inside. It's not relative to me. And yes, so this is this idea of quantum mechanics gives you, it's a machine to compute conditional probabilities, right? So the Born rules is really like, what is the probability of A given B? And what we do normally is, we apply this to classical probabilistic reasoning. This is just, tautology in probability. But in relational quantum mechanics, we have to modify this by adding labels to facts. So this rule works when I'm reasoning about facts relative to the same system. Whereas when I reason about facts relative to different systems, so fact A relative to Wigner, given fact B relative to the friend, then this doesn't work. This failure of probability, of classical probability theory, is the appearance of interference effects is a symptom of the relativity of facts. Then well, we have to explain how it seems like we share the same word, and this is this idea of stable facts. And so most of the time I don't see interference effects. I see like classical probability works, And of course, we all know this is somehow connected to the coherence, and this is very simple. So if it's a simple idea. If I have an entangled system, and it's entangled to the environment, so somehow it interacted with the environment, and maybe some facts were established between the system and the environment, but I don't have access to the environment. I only see the system. The object I use to make predictions is this reduced density matrix that, and if the different states of the environment are almost orthogonal, doesn't have any or approximately doesn't have any off-diagonal elements, doesn't have any coherence, right? And I can basically replace, let's say, the correct state that I should use with this diagonal state for all practical purposes and get back this notion of classical probability theory up to small deviations. And what's important to note here is that the coherence makes it only look like we share facts. Like I can reason as if there was a fact relative to Emanuele before that is also relative to me before I interact with him, but really the fact is established when I interact with the lab. And then it's also important to note that it's never complete, so this is always approximate reasoning. And another thing that is, I think, very important to understand this extended Wigner's friend scenario is that the coherence is not absolute, it's a relational concept. Like what I call the environment can change, is not necessarily what you call the environment. In particular, Alice and Bob have coherent control on the lab, whereas Charlie and Debbie, they were inside their lab, don't have coherent control, and so they see, this is what I like to think about different stability classes. So the friends inside are in a different stability class than the friends outside. And I also wanted to highlight this idea, this kind of troubling fact about that it makes it looks like we share facts, but there's no guarantee from inside the relational quantum mechanics, as I understand it, that we actually see the same thing. And this is perturbing. And Emily and Carlo talked about this in a recent paper. Maybe we can get it into the discussion. And just to conclude, I just opened some questions. So one thing I would like to understand better is how do we make sense of relative facts? And this is probably also really a task for the philosophers, what it means to be a fact and so on. And can we live like with this idea that maybe we don't see the same things? Then there is more technical questions. What is the relation with relational quantum mechanics with the Brukner-Zeilinger interpretation or Healey's, the proposals, cubism, Everettian quantum mechanics? These are all interpretations that embrace relative facts, but they're somehow different. We also need to reconsider Bell inequality because here now we're giving up the absolute facts. So the Bell theorems don't hold anymore. So these ideas of relative causality, of violations of causalities are not that clear anymore. And finally, I wanted to highlight that the general probabilistic theories, the process matrices, and the quantum reference frames that we talked about today are not really equipped to deal with the relative facts. Even the gravitational quantum switch doesn't really do with the relative facts. And maybe the only way, that's it. I will leave it like that. Good.
Thank you, Andrea. So from one member of the Vienna group to another member, in fact, the pillar of the Vienna group, Caslav Brukner.
Okay, do you hear me or you hear me well or not? It's working? Okay, good. Let me start by thanking your organizers for inviting me here and giving me an opportunity to take to express my opinion about being a friend situation. I call this objectivity bubble. The term is due to Eric Cavalcanti, the bubble, and I hope you will see why it's called like that until the end of the talk. So in my talk, you will see a lot of those things, and where I have a system, and then I have something which I will call experimental context or observation. There is also an agent, an observer, but I will not insist on this last concept. It's not, at least in this community. And I also talk about facts, and the facts will be very fundamental facts. What I mean with the facts is really like flashing of the light in the lab, detector click, somebody punching you into the face or something very rudimental. There is maybe even finer definition of facts, but I will not go until the end of talk almost into that, because this is sufficient. I think there is no disagreement that these are the facts. And also I need some kind of working definition of the objectivity under inverted commas. I would say that the concept here is called objective if this concept can be specified independently on the concept of measurement, observation, or experimental concept. And then the question is, of course, are the facts objective in that sense? Now, I would like to start with a kind of a game that resembles the situation in quantum mechanics, that we have some kind of epistemic restriction, for example, due to Heisenberg uncertainty relation, that an observer can observe just two possibilities, two variables, x or y, but never them together. So either if she chooses to measure x, she will get some statistics about outcomes for this choice of the measurements, or maybe another different statistics if she chooses to measure y. Now, in classical physics, and this is, I think, important, the observed statistics can be understood as marginals of the underlying hidden, because there is an epistemic restriction, hidden joint probability. That means that whatever she can observe is just marginalizing some, maybe hidden joint probability from which there is marginal emerge. And these joint probabilities, moreover, can be defined for all possible measurements that could be performed, no matter whether any measurement and which measurement is actually performed. And in that sense, it is objective. I don't need any specification of measurements to introduce these joint probabilities. So we have, in the sense of the definition, objectivity in classical physics. Now, I would say that in Kochen-Specker and Bell's type of no-go theorem, they show us that observed probabilities cannot be understood as marginals of underlying hidden joint probability, assuming non-contextuality, local causality, free choice, or whatever additional assumption you need to derive these no-go theorems. I will not give a justice and follow any of these options. I will take here the position because I have just 15 minutes, and that's what I would say what Bell inequalities tells us. So there is no underlying joint probability from which I can derive these observed probabilities. And in that sense, very particular sense, I would say these observed probabilities are not objective. I cannot say what is the probability to obtain outcome X of position X without specifying the whole experimental context of measuring the position. Now, there is a little bit of something unsatisfactory in the Bell's theorem, because the theorem involved definite outcomes of measurements the observer did not make. For example, the joint probability I introduced, but the observer has epistemic restriction. So the question is whether we can go beyond that and derive some limits on the notion of objectivity solely on the basis of performed measurements. And that's the point where Wigner's friend situation becomes interesting in my view. And I just remind you, and thanks Andreas for introducing this before, we have an observer performing certain measurements in a sealed experiment, and by observing a specific outcome, the friend updates, makes just state update. When I say collapse, I don't think about any physical collapse of the state, but just state update, knowledge update if you want. And whereas the Wigner, who is outside, can describe the whole process unitarily. And that's why we have, at the end of the day, different descriptions of what's going on in this physical situation. On one hand, a unitary one that will just entangle the system and the friend, or a measurement apparatus. This cat means everything that can correlate with the outcome in the laboratory, the whole physical situation, the environment, the notification in the lab book or whatever, whereas the friends indeed introduce, well, updates or depending on the measurement observed. So that's the original Wigner's friend situation. Now in '85, David Deutsch came up with a very nice twist on the whole situation, where Wigner himself also performs the measurement. So you see that there is a two level of measurement. And now, not only that this is a difference that Wigner performs the measurement, but Deutsch also allows friends to communicate to Wigner, a very subtle communication, the communication that doesn't reveal the outcome that has been performed and therefore doesn't change the superposition state as given by Wigner. And this message could be, well, dear Wigner, I have performed X measurement and obtained a definite outcome. And now that's the point where Wigner can start to think and say, well, I have performed a measurement, we both perform measurements, and each of us observed a definite outcome. It's so natural to assume that both outcomes must coexist. Now, there is a set of no-go theorems that I would say can be understood in terms of objectivity that I introduced before, namely, saying that the Franz and Wigner's observed probabilities cannot be understood as marginals of underlying hidden joint probability, assuming locality, universality of quantum theory, and depending on which no-go theorem you prefer, many other assumptions as well. Now, this shows us that in quantum theory, the probability distribution of the outcomes, which are now facts here, cannot be considered objective, not even for the measurements that are carried out in certain senses carried out. Now, there is a set of people, some subset of papers that deals with this situation, and I want to stress that the 2020 experimental and theoretical paper is, to my understanding, the strongest no-go theorem so far. And one way to understand these results is indeed to go into the two relative facts. And in my understanding, the notion of the Heisenberg cup, and therefore everything which follows from that, for example, the notion of system, quantum state, environment, measurement, unitary, collapse, irreversibility, outcome, are all relative to observation. And now I add this Cavalcanti's notion of bubble, which seems really a box in which the observers are. So they are all relative to a bubble, and within a single bubble, all these nations are effectively objective. Effectively because they are relative to bubble, and so all observers within the bubble can have intersubjectivity of that notions and can agree. And furthermore, it's consistent to have both collapse for the friend and unitary for the Wigner, because these are notions that apply to different bubbles. There is no problem of having them both referring to the same physical situation if they are seen from different bubbles. Now, I tried now to summarize those interpretations that share the view of or accept the possibility of the facts being relative, and that's relational quantum mechanics, cubism. I would also add something neo-Copenhagen. I'm less sure about many worlds, and I will not say anything about that, as contrasting them to those that accept absolute facts like Bohmian mechanics and collapse models. Now, what is I would like to stress, what is certainly very remarkable, that people who propose, like Carlo, relational quantum mechanics, or Chris for cubism and his co-authors, came up with the idea of relational facts even before no-go theorems forced us to accept them under the assumptions. However, these three options are distinct to each other regarding the question of what these facts are relative to. And relational quantum mechanics says that they are relative to other physical systems. Cubism says that they are relative to agents' personal beliefs, and neo-Copenhagen, in which I will broadly put also myself, say that facts are relative to experimental context. And this gives rise to possible quantification of this distinction, and to something where I would like to tell you at the end more about how these relative facts could be understood. Now, relational quantum mechanics starts with a very reasonable view and main premise that all quantum systems are equivalent. So there should be no essential difference between the left and the right-hand side picture, between the relative effects, correlations between the qubit and the apparatus, or qubit-qubit system. And from now on, I will use the word observer, but in very abstract sense, meaning measurement apparatus, or meaning the other qubit on the right-hand side. I don't impose anything more than that. It's just the way how I would want to distinguish subsystems. Now, relational quantum mechanics goes a step further than that. And realizing that we in the laboratory situations have something which we call the quantum measurement problem, or if you want, ambiguity of where we should apply unitary evolution and when we should apply measurement update rule, moves into the saying that this situation is not different than the situation between two qubits, tries to remove this ambiguity because in the two qubit situation, we don't have measurement apparatus in the first place. So therefore, should be no distinction between the unitarity and state update rule. I have a concern about that, and I understand that this talk should be also a little bit controversial. And in my view, the attempt to map the situation from the laboratory scenario into the qubit scenario, let's say, rather introduce the measurement problem also at the qubit level, because the questions arise like when the facts happen, or under which conditions, or in which phases. Now, this is the distinction between the two cases. In both cases, we start with the same formal quantum states, entangled states, between the system and apparatus, or between two spins. But on the left-hand side, we may associate this state with a statement. The statement is that the spin of S is up or down relative to the z-axis of the laboratory, for example, if this up and down corresponds to the z-axis. And the states of the measurement apparatus are orthogonal to each other. They're identified as distinguishable on the macroscopic level. And the basis that we write here, this state in, is some preferred basis, which is given either by some decoherence or by the macroscopic apparatus that we use, or even in cubism by the agent's beliefs, the states of the agent's beliefs. On the right-hand side, this first insight, we think that we don't have a well-defined basis in which we want to express these relational facts. And we might ask ourselves, given that these are the states of two spins, in relation to which direction is the spin of one qubit up or down, or parallel or anti-parallel with respect to another one. This gives rise to possibility to quantify the difference, and this is not a critique of relational quantum mechanics, it's rather trying to pinpoint the difference between notion of relative effects in relational quantum mechanics and in cubism or neo-Copenhagen point of view. And here is the way to do it. I also refer to Jacques Pionard's paper from the last year. The first definition, you don't need to read everything here, is the definition of what knowledge of the observer is. And I say observer in very general sense, abstract sense, even if I may assign this to qubit. And this tells you that you need certain correlations between the system and observer in order even to say that observer has some knowledge about the system. And I would say that whenever, for any set of states for which I can write a given state of system and observer in this form, I would say, well, the states of the capital Xi are states of knowledge of the observer, the knowledge about a small letter xi of the system. And so when the observer is in the capital Xi, she knows that the system is in the definite relative system Xi. The second, and this is just, I think, not very controversial, that wherever we want to gain some knowledge, we get correlated with the system. The second one is something which I would say the distinct relative states. And then I would say that the observer states of knowledge, for example, x prime, which are correlated with distinct relative states of system, distinct, not necessarily orthogonal, just distinct, should be represented by orthogonal vectors in the observer Hilbert space. So even if if these two states are not the same, nevertheless, the observers should be orthogonal. Why? Because if we perceive something as different, we have a distinguishable states of perception, which are macroscopic states, and as distinct perceptions should be represented by orthogonal states. Now, it turns out that if you have a qubit situation, you cannot fulfill 1 and 2 in general. So qubit states cannot be understood as a state of knowledge in the terms of these definitions 1 and 2. And furthermore, this knowledge, even if there exists, is not this standard knowledge where we think about orthogonal states or classical representation of classical information that can be copied, that can be communicated. That's what we understand under usual circumstances as knowledge. So this pinpoints a difference, I would say, between the laboratory situation and qubit situation, and bring us back to the question of ambiguity of the basis representation. So the observer's states, in the case of qubits, could be also spin up, but also spin along x direction. They are not orthogonal to each other and cannot be considered in that sense as knowledge in terms of the definition 1 and 2. So it remains ambiguous to which base the relative factor refers. Now, there was a very nice twist this year, Emily and Carlo wrote, as I think a possible reaction to this, that the alternative is, and I quote here, the alternative is to agree that quantum emits do not typically have the simple form, variable v taking value v relative to Alice. Rather, they must have a conjunctive form, where you have a series of statements like variable v1 taking value v1 relative to Alice, and variable v2 taking value v2 relative to Alice, and so on. The way how I understand this in terms of the example that I gave is that we should think, for example, about the singlet as a conjunction of the statements that the two spins are antiparallel along all possible directions. And I think that tells you first that it's a different kind of representation of knowledge. I don't know whether I will call it knowledge, because it's not the knowledge in the sense of the no-go theorem. However, I will also want to give a warning. And the warning is that this step was one of the premises of the EPR program. And one should be careful when doing that. I think it's possible not to fall into the hidden variable trap. And just to remind you what are the EPR assumptions, is that you have perfect correlations along all possible directions. And you think that all are true, that all exist in certain sense. You add to that locality in reality, here written in the EPR original, and you are in the hidden variable trap. So one should be careful not to make too much, two additional steps that can bring you in this danger, I would say. And here is a proposal. This is the last my slide. I feel like we should take the best of all worlds. And I would say for the relation quantum mechanics, we should retain the relational notion of events. That's a very important message. But I would reject the idea of macroscopic-like world at the level of qubits. And I will be, in the last sentence, more explicit of that. But this mapping of the laboratory situation and using the language of the laboratory situation, the qubit, I think, is narrowed down, and I'm not sure we can come out of it in a consistent way. I would like that we retain the idea that quantum theory gives the description with respect to the observation. It seems to me that the observation is an important step within the bubble, if you want. But I would like also to go beyond that. Maybe what was the initial idea of relational quantum mechanics, to go beyond laboratory situations. But when we are doing this, we should take seriously that a few qubits do not have enough resources to define a spatial direction. And hence there is no meaning in using the notion of directions and saying one spin is antiparallel to another one or is along the other one in relative X. And with this, I would like to thank you for your attention.
Thank you, Caslav. And one more speaker, Richard Healey. So to complete our introduction to the discussion about objectivity, we needed a philosopher point of view.
Thank you. Is the mic on? Yes. Good. Well, thank you to the organizers, and thank you to the people who gave the previous two talks, because they've set things up really nicely for me. So you won't get to hear my little story about Adele and Brian to introduce the notion of challenges to scientific objectivity. So I'll just go to the main points I want to make. And as a philosopher, I find this situation presented by no-go theorems in the context of EWFS scenarios really interesting because of the challenge it presents to the notion of a fact and the notion of objectivity. In correspondence, electronic correspondence with Eric Cavalcanti, he tried to persuade me that there's really no issue for objectivity. It's all about relative facts. And I said from the beginning, no, relative facts that don't really matter so much. It's objectivity that's at issue. Finally, I think they're both at issue here. So the interesting question is, what do you mean by a relative fact? What do you mean by objectivity? What's the relation between them? And what can we do to rescue scientific objectivity in the face of the no-go arguments based on EWFSs? So let me first start talking about objectivity. And indeed, the first part of my talk is going to be very general and very philosophical. So the first thing I want you all to do is to forget physics. That might be difficult in some cases, given there are so many physicists and they think about physics all the time. But the issue of objectivity and the issue of facts come up much more widely than in physics. And I'm going to begin with a very general discussion to build a general framework that I can apply to the EWFS scenarios. Okay. So I'm going to say objectivity, or the distinction between objectivity and subjectivity, depends essentially on the contrast between object and subject. That's not very surprising. And the key to claims to objectivity is independence of the subject. Independence of what? Well, I'm going to say a belief. So the belief, I think, is objective if whether it's true doesn't depend on the one who assesses it. Now, of course, that leaves a whole lot of issues completely open. What do I mean by one, for example? What do I mean by depend? But the contrast, before even going into those questions, is clear because the belief is subjective if whether it's true depends on the one who assesses it. And I think that science rests on objectivity because an observation report's assessment, is it true, is it false, does not depend on the one that believes it. If two experimenters sharing the same lab give different assessments to the truth value of an observation report made by one of them in that lab, then science is off to a really bad start. At some point, we have to take something as data. And if we can't at least come to intersubjective agreement on what the data is, then we're going to find it very hard to provide evidence for any scientific theory based on that data. That's very brief, but things will become clearer when I narrow down to the context of extended Wigner's friends scenarios in the second part of the talk. So next, I want to go on to facts, and in particular, what a relative fact could be. But part of my resistance to talking about relative facts in this particular context was I had no idea what a relative fact could be. It's only when I finally convinced myself I could give a story about what a relative fact might be in general that I was able to find a place for relative facts in discussions of EWFSs. But we have to start off by the notion of a plain common or garden fact. What is that? It's not the kind of question physicists spend much time thinking about, but philosophers have spent quite a while thinking about it. And I think that there's an important, even essential connection between the notion of a fact and the notion of truth. So here's what I think the connection is. A statement expresses a fact if and only if it is true. Well, that's fine, but what is it for a statement to be true? Well, over the ages, philosophers have given all kinds of theories of truth: correspondence theory, coherence theory, a version of a-pragmatist theory, truth is what works. I'm going to be much more modest and take a deflationary attitude to the notion of truth, and take it that the core idea behind the notion of truth is stated by this principle: a statement that P is true if and only if P. That's rather dull, it's rather boring, but it gets to the essence of what truth is all about and doesn't send you off on wild goose chases talking about correspondence theories of truth and coherence theories of truth. So replace the symbol P by anything you like. Snow is white, today is Wednesday. I'm talking to you now. Okay, and then you get an instance of the truth schema. Okay, so far so good, but so boring. What about relative facts? Well, I think you can state analogous principles for relative facts and relative truth. If you do, it looks like this. We relativize truth itself to a context of assessment, see, a context in which one can imagine someone assessing a statement to decide whether it's true or false. Each of you right now perhaps is in such a context, wondering whether what I'm saying is true or false. So if we relativize the first principles for truth and fact, we get relative fact. A statement expresses a relative fact if and only if it is true relative to a context, but neither true nor not true. Notice there's a little sting in the tail there. If this is right, no relative fact is a fact, because to be a fact, it would have to be true. And in this notion of relative facts are neither true nor not true. And relative truth, what's that? Well, I played the same game I played with truth. A statement that P is true relative to a context of assessment, if and only if P relative to that context of assessment. So to the extent that we understood facts and truth, we're now supposed to be able to understand relative facts and relative truths, given that we know what we're talking about when we're talking about a context. And that's going to be very important in application. Okay. Now, again, this is just a framework, and we haven't yet focused even on science, except for my one remark, perhaps motivating the present project. So what is then the connection? Or actually, let me go back up to objectivity, which is my main concern here anyway. Now we can understand objectivity in terms of facts and relative facts. Okay. And here I'm going to distinguish two kinds of objectivity. The distinction is going to be important when we get on to EWFSs. So a fact is absolute, that's most people's term. I use this fancy term, transcendently objective. If its assessment is true, has nothing to do with any context of assessment. Okay? And I will say that a relative fact is eminently objective if it is true relative to every actual context of assessment. Okay? So we have two distinct notions of objectivity here that we have to play with. And I'm going to tell you, to jump ahead to the punchline, that science depends on immanent objectivity, but not transcendent objectivity. And I believe, although I may not be able to convince you, that we have immanent objectivity of relative facts, even in the extended Wigner-Strand scenarios. Okay. So the claim is that science depends only on immanent objectivity. Why? Because the relative truth of an immanently objective observation report doesn't depend on the context at which its relative truth is assessed. Okay, that's going to be where I'm going to with all of this stuff. Now, I didn't tell you what I meant by one. Okay, a subject. What counts as a subject? Well, a conscious being, a physicist with a PhD, any agent, any organism capable of agency. It could be anything. It's a gap that you want to plug with one of those notions of one, the subject. But there's got to be a subject if we're going to be talking about the distinction between subjectivity and objectivity. Could even be a measurement context, although I don't think I want to say that. Okay. And then what about the notion of dependence? I should go back to my definition of objectivity. Okay. Whoa, I was going forward. Let's try again. Okay. What is it for the truth to depend on the assessor? Well, it could depend on the identity of the assessor. There are cases like that where subjectivity becomes an issue. It could depend on the circumstances of the assessor. The assessor, the subject, may learn more or may change their evaluation and assess things differently on the basis of additional knowledge or additional evaluations in some sense. It might even be independent of the existence of any assessor. That would be a very strong notion of independence. I think that Karl Popper, for example, thought that scientific knowledge was objective in that very strong sense of being completely independent of the existence of anyone who's in a position to assess it, something often some Phrygian realm or something. Okay. So that's the general scenario. If we're going to apply it, we have to say what we mean by one, what we mean by dependence, and what we mean by a context if we're getting into the relativized notions of truth and fact. Okay. What is a context in an extended Wigner-Strand scenario? It could be a system. It could be a laboratory. It could be an individual conscious scientist inside or outside the laboratory. I'm going to take it that a context, well, let's go through the list. I have it here, right? I take it that a context is not provided by the observer's consciousness. If there are two observers in the lab, it doesn't make any difference. I don't even think they have to be conscious. There could be a recording device, which counts as, from this point of view, providing us with a context in an extended Wigner-Strand scenario. Is it the observer's lab? That's looking a bit more plausible. I'll come back to that. Is it the observer's lab's post-measurement condition? I think that's getting closer to it. The context changes during the performance of the measurement, and that's important to bear in mind. So we shouldn't be relativizing systems to, relativizing truth and facts to fixed objects just because the relevant context changes. I'm going to take it, and I'm really specializing towards my own view, as you can take a context to be a context in which the Born rule yields probabilities. That's the key notion. Probabilities for outcomes in one or more isolated labs. I actually want to extend it even beyond that to nature. Forget about labs, but that won't be important today. And in my view, that is determined by decoherence. Okay. So for me, a context in an extended Wigner-Friend scenario is going to be what I call a local decoherence context. Local in the sense of local within a supposedly isolated laboratory, or maybe a pair of supposedly isolated laboratories, or more broadly, including various bits of the external environment of all of those. They would each provide different decoherence contexts here. And I take it it's the character of decoherence processes that sets the context for application of quantum theory, and thereby the Born rule. And by doing that, it sets the context for assessment of statements about the outcomes of quantum measurements, which I'm going to call Q reports. Okay. So now we know what we mean by a context of assessment. Then we can start applying the general framework that I laid out in the first part of the talk. And the first claim then is that given that notion of a context, the report of an observation of a quantum measurement expresses a relative fact if it is true only relative to a context. And just to repeat, a Q outcome occurs in a localized decoherence context in which the Born rule may be applied. So I'm diverging now from relational quantum mechanics, which uses decoherence in a different place in the overall story. I'm closer to what Caslav was saying, although I don't like to be called a neo-Copenhagenist, I have to tell you. In any case, a Q report in an extended Wigner-Friend scenario is relative to multiple contexts. It's true relative to some, with this notion of relative truth, and it's not true relative to others. But if you go back to what I said about objectivity, we still have a problem, because science depends only on immanent objectivity, and I've just said that the relative facts which figure in EWFSs are not even eminently objective, because they're not true relative to actual context of measurement in the extended Wigner-Friend scenarios. But if I've said here that science depends only on immanent objectivity and we don't have it, then we're in big trouble. So what are we going to do about it? Well, I have a proposal to make to you. I feel a little guilty making this proposal because I have underlying faith that it's true, but I can't prove to you that it's true. Okay. The features of decoherence are adequate to ensure its truth. Okay. So the claim is that nobody will ever perform an extended Wigner-Friend scenario experiment. That's a very strong claim. And the first thing I expect you to say to me is, well, it's not in violation of any physical law. I agree. It's not in violation of any physical law. And we're pretty smart, and given progress in technology, we'll finally get around to doing this. I think you won't, because the character of decoherence processes in our actual quantum world puts everyone in a single context of assessment at the end of the day. What does that mean? Well, we're worried about immanent objectivity. If, in fact, there is no possibility, in my sense of possibility, performing an EWFS, then we're effectively all in the same context here. And if that's so, then the relative facts expressed by outcomes of observations, quantum measurements in an EWFS are immanently objective, because they're true in every context of assessment. Because there's only one context of assessment, our context of assessment. That's why science is okay, despite the threats posed by EWFSs. Okay, shut me up if I'm going too long, please. So one thought that might occur to you is, look, people have performed experiments. The Bohm paper that Caslav alluded to, and the Proietti paper, these are experiments which are supposed to be at least proof of principle experiments for actual EWFSs. Well, I don't think they are. here's the schema for the Bong experiment. Okay? Very little of this complicated diagram is relevant to what I'm saying, so don't let your eyes glaze over. That's my intent to do when people put up complicated slides like this. Okay? So all the stuff on the left is just preparation. The measurements, if any, occur on the right. And we had two friends, Charlie and Debbie, and we had two Wigner clones, Alice and Bob, outside. And if there's such a thing as an observation by Charlie and a corresponding observation by Debbie, they occur sort of near the D-shaped mirrors and the interferometer there. Okay. And if Charlie, for example, on the left-hand side here, sticks the mirrors in, that's taken as an observation of the position of a photon going through the left-hand side of the experiment. And similarly for Debbie on the right. So the objection to this is, well, look, there's no actual measurement being performed by Charlie in that situation. What's supposed to be happening is Charlie's performing a measurement, and then the measurement result in his lab is supposed to be rewound unitarily before continuing on to what Alice and Bob do later. Okay. But in fact, that's not the case. There is no Charlie here, and the path of a photon is not an observation. Because there is no observer and there is no decoherence present to ensure the existence of an observer. Now, I hasten to add, this is not a criticism of the paper. They don't say this is actual realization of EWS, but they do claim it's a proof of principle. And here's a statement from the paper. If universal quantum computation and strong AI are both physically possible, it should be possible to realize quantum coherent simulations of an observer and its virtual environment, and realize an extended Wigner's friend experiment. I believe today that that's false. I believe that the conditions necessary to do that are wildly beyond any abilities of any future technology that we or any other agents could come up with. But this is a challenge, right? Prove me wrong. If you succeed, then we're in trouble with scientific objectivity.
Thank you so much, Richard. And let's take a break, half an hour, and be ready for the discussion